Today, my colleague Yusuf Adib and myself, Mohammed Al-Ibshihi, will be presenting to you our steps in order to model our intermediate fluid mechanics project, starting with the model wizard. Then we go to the 3D option, and then we choose the fluid flow, single phase, laminar flow. And then we add study, and our selected case study will be stationary. Done. Okay, first thing first, we'll choose our length unit will be in millimeters, and then we'll build our project is to model a blood vein, which is diagnosed, and our first geometry that we'll start with is the cylinder, and we'll set the length to be the height will be 10, and it will be in the x-axis. That's selected. Alright, and then we'll model our spheres. So we'll go to the geometry and then we choose sphere. Our first sphere will be of radius 1.5, and we'll place it on halfway through the cylinder, so it will be x is 5 and y will be 1.7. And then we build. And then our second sphere will be on the other side, which should be symmetrical. So it will be also 1.5 radius. X is 5. And y is negative 1.7. And build. Then we move on to the Boolean and partitions difference. We'll select the sphere. And then for this, we'll select the two the first one we select the cylinder, and for the second one we select the two spheres. And then we create our first study. And then yes, these are two fluid properties. Now we'll determine the fluid properties, which is usually a blood. And in this case, we'll use a user defined. And then for the viscosity, user defined, and then 0.004. And now I'll hand on to my friend, Yusuf Adib.
Appreciate your explanation. I hope that you guys are following us so far. So now that we have completed the initial setup, our objective, of course, is to conduct the mesh analysis to perfectly understand how would the flow be inside the vein that we have completed so far. So our first step would be that we would go over here to the wall selection, and then we will move to wall movement. After being in wall movement, instead of having an automatic from frame translational velocity, we will make it such that the translational velocity is 0. So it's as if it's a fixed wall. Having done that, we will go over to physics. Over here, physics. Inside of physics, we'll go over to boundaries in order for the software to understand the inlet and the outlet of the vein. So we have the inlet option over here. Having selected that, we will go right here exactly at this point, and then we will set the inlet velocity as 0.6. Okay, so now that we have selected the inlet velocity, of course, we also need to select the outlet velocity. So it's exactly the same concept. We'll go over here to boundaries, then to outlet. In this case, of course, we will need to rotate the frame in order to access the outlet, which is located over here. Having selected the outlet, once again, we have on the left hand side the parameters that we need. However, we won't make any modifications. So now our focus is to compute and conduct the mesh analysis. So we'll go over here. We have the name of the study, which is in this case selected as study one. We can change it to whatever name we need. For example, instead of having it as study one, we can name it as vein blood circulation. Okay, so now that we changed the name of it, we will go over here to compute. And computation time, of course, is depending on the complexity of your geometry and like the geometry of interest. Sometimes it can even take like up to many hours in case you have a very complex geometry and you are expecting, for instance, to model a very like complex flow. In this case, it would take up to like many hours. But in our case, as the geometry is quite simple, it shouldn't take more than a minute or two. So over here, we can see the loading time and the completion progress of the meshing. So we can wait for it a little bit. And once it is done, we will see that we will be able to get a perfect representation of exactly how will the flow look like inside the vein. So it's almost done. It's very near to the end of the process, the meshing process. So here, finally, we can see exactly the velocity profile inside the vein. So on the left hand side, we can see that we have a results section. And this results section, of course, is key. It's very important because it's the one where we would be able, for instance, to generate streamlines. It's the one where we would be able to study the velocity at certain points and get values for that. And it's really like our focus right now. So after meshing and after the step of like studying and drawing your geometry inside the software or even in another software and importing it, your focus would be over here in the results section. So we would go into velocity, and we already have what we call here as slice, which represents the different planes at different instances of the vein. But our focus would be to add, first of all, a new slice from here inside the add plot configuration. We'll go over here, add slice. So we can see that the new slice is named as slice 2, and slice 2 right now is in the YZ plane. In this case, of course, we are more interested to have it in the XY plane rather than having it in the YZ plane. So having done that, we will modify the number of planes, or actually we can keep it even to the same number, and then we would go and ahead and plot. We can see that over here, for instance, this is what it looks like when you have 5 planes. So for simplicity, in this case, we can just stick to one plane because that's what we are interested in. Can go over here once again, plot. We can see that now the modeling is much cleaner than before. So of course, once again, this is depending on your application. There is no specific rule for that. Having finished that, we will go to streamline. So over here, streamline. And here, of course, the focus is to study exactly the velocity profile of our geometry. So now, right now, the positioning is on selected boundaries. Instead of having it on selected boundaries, we will go with this option, which is starting point controlled. And yeah, we can just see, the beautiful streamlines that we have. So once again, the colors, you can modify them depending on your preference. Right now, the streamlines are represented in a red color. You can make them in magenta. You can make them in blue. So it's really based on your preference. For now, we can make them yellow, for instance. Over here, we can see the streamlines exactly describing the motion inside the vein. So having completed this key step, we also have an advanced option. For instance, in order if you would like to have a limit for the length of the streamline, or for instance, if you would like to integrate a certain tolerance. In our case, this is not of interest. Our focus would be mainly, of course, just to plot the streamline. So now we can go over here even to show you that if you would like, to disable the streamlines, you can do so very easily by just a click of a button over here, the disable option. So right now they are disabled. If you would like to enable them again, you can have the enable option and just, go ahead and enable them once again. It's really based on your preference. It's really based on the application you have and on the study you are willing to conduct. So having that behind us now, we can see actually that our geometry now is much more clearer. We have divided it into five different planes, and these help you once again, to understand exactly the parameters and how they vary inside the vein. We even have the option to zoom at a certain area, for example, using this option, the zoom box option. We can go over here and we can see that the velocity at the center of the vein and in the middle is would be at its maximum, so that this color of course represents the velocity magnitude as indicated over here in meters per second. And as the color is more it's closer to red, it means that the value is higher, and as it becomes closer to blue, it means that the velocity is decreasing or lower. We can, of course, as usual, go to the full view by pressing this option. So the idea, of course, once again, is that we have the option and the ability, to model the flow inside any geometry that we are willing to have. And we believe that COMSOL is a very good software to do so, very user friendly. For us, for instance, this has been, one of the few times we have used COMSOL, and you can see that it's very direct. The options are very easy to understand, and we would truly, like recommend it for anyone that is starting any CFD project or that has to conduct any CFD study. So we can enable them once again just for the sake of it. Honestly, I don't really like the yellow color, so we can change the color of the streamlines. We said that we can change them from here, color. We can make them, for instance, blue, which is, I believe, more visible in this case. And this is the idea. This is the idea of our project. This is the idea, the main idea of COMSOL. It's very straightforward. We strongly recommend it for anyone that is willing, to try and experiment with the CFD software that would be like very perfect. And we can even have specific points if that's something that we want. So over here, we can see streamline positioning. Right now, we have 20 points. We can add them, for instance, to be 55 points, and then go over here in the plot option. We can see now that the streamline is much more complex. We have a much more detailed representation. And we can even do the opposite, for instance, and have the number of points as 20 point as sorry, we had it as 20 initially. We can have it as, let's say, 10 points. That would be good. As 10 points, you can see that the configuration is much simpler. So it really relies on the user. It really relies on how you would like to represent the flow. Honestly, I prefer for now, for instance, to represent it with 45 points, just randomly. Let's see. Yeah, I believe that looks nicer to represent the flow in this case. And once again, as we can see, we have the zoom in option that we can always use, for instance, to study a particular region of interest and see how exactly the flow differs compared to the other regions in our vein in this case. So that's about it. I hope that you enjoyed our video. I hope that our explanation was clear and that you were able to model along us the flow of the blood inside a vein, and that you were able also to understand the main fundamentals of this project. Thank you very much. And once again, I would like to invite my colleague, Muhammad Ali Bshi, to thank you.
Thank you guys. Hope you enjoyed the video.
All right, perfect. Thank you very much, guys, and have an amazing day. Thank you.